we're going to hit the next topic in this unit, and that is something called synaptic potentials. So up to this point, we've really just been talking about action potentials, which is what happens when that neuron is depolarized enough, it hits that threshold at negative 55 millivolts, which triggers this thing called an action potential. And once you hit that negative 55, off to the races. There's no stopping it. So an action potential is what we consider all or none, and when it occurs, that's it. It goes. There's nothing stopping it. But what I haven't talked about yet is what causes it to hit that negative 55, right? I keep saying I'm going to get to that. Well, here we go. We're going to get to it. So this is called a synaptic potential. So basically, if you go back to earlier on in this unit, I mentioned that there's different types of channels, right? We have different types of gates. We have ligand-gated channels and we have voltage-gated channels. Voltage-gated channels open when there's a change in the membrane potential. So if it's negative and it switches to positive, that change in potential causes the change of the protein to shift, and that opens up the channel. The second type that I've talked about were these ligand-gated channels. And ligand-gated channels, they open when there's a chemical, like a neurotransmitter. So that's what this first couple bullets here are talking about. So when the channels respond to a chemical, like a neurotransmitter, they're going to be chemically or ligand-gated. And what ends up happening is you're going to have this small change in that area called the synaptic potential. And what that does is it allows one neuron to influence another neuron. So it's what makes one neuron talk to another. So if I look at this diagram here, this would be where the synaptic potential occurs in the cell body, and then the action potential happens in the axon. So this neuron would be communicating with this neuron. Synaptic potential would happen where the synapse is, and then you have your action potential going down the axon. So if I bring up that diagram that I've been working with a lot in here, what does this have to do with this? Well, basically, what you should think of is this as I said before, we have our axon down here, and we have our cell body up here. On the axon, we have our voltage-gated channels, and they open when there's a change in the membrane. And then in the cell body, which is going to include also the dendrites, because remember, the dendrites are attached to the cell body, these are voltage-gated channels. I'm sorry, these are ligand-gated channels, which means that they open when there's a chemical that attaches to them. So just like when troponin attaches to calcium, it changes its shape. Well, when a neurotransmitter attaches to a ligand-gated channel, it changes the shape and it opens it, or it closes it, depending on the scenario. So let's talk about the different types of synaptic potentials, because there's two different types. The first type is called an EPSP, or an excitatory postsynaptic potential, and the second type is called an IPSP, or inhibitory postsynaptic potential. Whoa, right? That's a long word. That's a long term. It kind of sounds like it's going to be really confusing. Well, don't worry. It's more confusing sounding than it actually is. So excitatory postsynaptic potential. What the heck does that mean? Well, excitatory, to excite something means to make it happen, right? To inhibit means to prevent it. So an excitatory postsynaptic potential is going to trigger a response. Postsynaptic just means it's the neuron after the synapse. So this is the neuron that is being stimulated. And then potential just means change in membrane, right? So what is the EPSP? That occurs when a neuron is more depolarized or becomes less negative. It doesn't hit that negative 55, but it becomes less negative. So that would be an EPSP. So you don't have your action potential yet. It doesn't get to negative 55, but it gets closer to that level, and then it's able to have an action potential easier. An IPSP, on the other hand, does the opposite. An IPSP occurs when the neuron becomes more hyperpolarized or more negative. And what that's going to do is make it less likely for an action potential to occur. And then what ends up happening is the type of neurotransmitter is going to determine whether it's an IPSP or an EPSP. So if you look at this diagram down here, this little chart, it shows you. So this would be the action potential threshold right here. It's listed at negative 40 because like I said, all these numbers are kind of different depending on who tells you. We're using negative 55 and we're using negative 70 as resting potential. So let's say this is negative 70, this is negative 55. And EPSP is going to get it closer to an action potential, so it's going to make it more positive, and then an IPSP is going to make it more negative or farther away from an action potential. And then this idea of summation I'm going to talk about in a moment. So let me explain this a little bit better with this diagram. So let's say I have a neuron here that is at resting potential, negative 70 millivolts, right? We have our negative on the inside, positive on the outside. So in order for us to have an action potential, this has to get to negative 55 millivolts. And that is going to trigger this channel to open, and then we're going to have our action potential go all the way down the axon. So how do we get to this negative 55? Well, that is going to be what happens with the synaptic potential. So let's go with our first example, an EPSP. So an EPSP would be excitatory, and an EPSP is going to open a sodium channel. Okay, so what does that mean? So an EPSP would have a neurotransmitter that's excitatory. So acetylcholine, for example, is an excitatory neurotransmitter. It's going to attach to a sodium channel and open it, and some sodium's going to come in. So you're going to get a little bit of sodium building up. And when that sodium comes in, it starts to make this area right here more positive. So it's going to get like a little more positive. So maybe it gets a negative 65 millivolts. Still not negative 55, but getting closer, right? And then let's say more neurotransmitters released, and we have even more sodium flooding in. And it gets to this area. Well, now it's becoming even more positive, negative 60, and then eventually it'll get to that negative 55 and we'll have an action potential. So this would be excitatory because it's making the neuron fire off. What is an inhibitory neurotransmitter then? Well, an example of that would be like GABA, right? GABA is an inhibitory neurotransmitter. That would attach to a potassium channel. So it opens a potassium channel. And just like in the axon, there's sodium and potassium in here too, the potassium's going to leave. And when the potassium leaves, that's going to make this area more negative again. So it's going to get away from it. So for example, if it's at negative 70 at rest, when that potassium leaves, it's going to get to like negative 75. And maybe even more potassium leaves and it gets to negative 80. And it might get all the way to like negative 90, negative 100. And what that means is it makes it harder and harder for this neuron to have an action potential. So really you have to think of it as two different opposing forces, where the inhibitory neurotransmitters are preventing this neuron from firing off, and the excitatory neurotransmitters are telling it to fire off or causing it to fire off. And that is the difference between the two. So let's finish up here with a little more about how this works. So what are the effects of these IPSP and EPSPs? Well, if a neurotransmitter opens the sodium channels and sodium comes in, it's going to become more depolarized, which is going to be an EPSP. And if a neurotransmitter opens a potassium channel and makes potassium diffuse out, it's going to become hyperpolarized or have an IPSP. So here's the thing we have to all understand. Neurons are not living by themselves. Your brain is full of billions of neurons, and they're all packed together. And obviously, the neurotransmitters are being released, and it's not like one at a time. They're being released constantly. And what you end up with is you get a whole bunch of EPSPs and a whole bunch of IPSPs happening, and at any moment, the balance can shift. So I'm going to give you a little analogy that I think is a good one. You've all heard the scenario of the angel and the devil on the shoulder, right? High school's got a lot of peer pressure involved in it. So I know that, let's say you're standing up on a bridge, like up on a bridge, and there's water below you. And it's like a spot where people jump off. Like I know there's the locks down by Phoenixville, and a lot of people jump off the locks into the water. So let's say you're like, hey, I'm going to go up there one day. I want to jump off the locks. I see people do it. I want to try it. So you go up there with some friends, and you bring two of your friends. One of your friends is the goody two-shoes, and the other friend is the one that likes to get you in trouble. The devil and the angel on your shoulder. And you're standing there at the top of this bridge, and you're looking down at the water below, and you're getting kind of nervous. And you're just like, hey, I don't know if I should do this or not. I mean, what if there's something down there and I hurt myself? And you're not sure what to do. And you have your one angel over here, your friend that's the goody two-shoes, is like, no, don't do it. Don't do it. You're going to hurt yourself. It's not worth it. It's going to be bad, 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 bad. And then you have your other friend on this side who's being like, do it. I got my video. We're going to video it. We're going to be up on TikTok. You're going to be famous. Everyone's going to see you jump. And then who wins in that scenario? Whoever's loudest is going to win. If you bring more friends that want you to jump, you're probably going to jump. And if you bring more friends that tell you not to, you're probably not going to jump. So think of the friends that tell you to jump as the EPSP and the friends that tell you not to jump as the IPSP. So essentially, a neuron is getting both messages all the time. And it's just a matter of what is there more of. If there's more excitatory neurotransmitter, that neuron's going to fire off. If there's more inhibitory neurotransmitter, that neuron's not going to fire off. So it's a balance of those two things. And there's a term called summation. So if I go back to this diagram from that last slide here, You can see it happening here. If I have more excitatory, it's going to bring it closer to an action potential. If I have more inhibitory, it's going to bring it away. So it's a combination of those two which determines what happens. So synaptic potentials are graded. The more you have of one, the better chance you have of an action potential. So let's finish up here with a little bit more terminology, and then we'll be done for this lecture. So what are the big differences between action potentials and synaptic potentials? Well, synaptic potentials are graded, which means that the amount of neurotransmitter has an impact. So if there's more excitatory, it's going to have a bigger impact than if there's less excitatory. That's called summation, where action potentials are all or none. If you hit negative 55, it happens. If you don't hit negative 55, it doesn't happen. There's no in between. There's no gray area there. The other big difference is that PSPs, which are the postsynaptic potentials, they actually decrease intensity as they get farther away from the membrane. Where with an action potential, it stays the same intensity the whole way. Once you have an action potential, it's the same. It just goes, right? So it's that idea of all or none versus graded. So finally, there's a term called facilitation. So what is a facilitated neuron? A facilitated neuron is one that has been excited to a point where it's almost at action potential. So if I go back to my diagram over here, so for example, let's say I have a neuron here that is at rest, and I have added some EPSPs to the scenario. We've added some sodium, right? It gets a negative 65, negative 60. Let's say it's at like negative 58. This is a facilitated neuron. It just needs a little bit more to get to that negative 55. So what would that be like? Well, for example, if you warm up, if you're doing something active, or like if you're practicing for an exam, your brain is firing, your neurons are going to be facilitated. They're going to be ready to go because you've been adding more of that excitatory neurotransmitter. So a facilitated neuron is one that is close to an action potential but still sub-threshold. Okay, thank you very much.